Hello everyone. In this video, I'm going to review how to solve system of linear equation using both direct and iterative methods. I will also solve an example that show how to solve nonlinear simultaneous equations using the Newton-Raphson method. Before we look at how to solve problem using direct and iterative methods, we need to review a few concepts, including matrix norm, vector norm, and the conditioning number. Look at this vector. This is for vector norm. For vector x with this component, we are trying to find the norm infinity, norm 1, and norm 2. For finding the infinity norms, okay, we have to pick the maximum absolute value for maximum value of the components. As you can see for this vector, the maximum value, the maximum absolute value is 5. How about the vector norm 1? We are adding the absolute value of all the components together. Is 8. And for norm 2 is like as the physics that we learn is the square root of each of components to the power 2. Okay, this is about the vector norm. The subscript is showing we're talking about the which type of the norms, and this is the sign of the norms. Another thing is that we have to know that is a matrix norm. For example, for matrix A by 2 by 2 dimensions, we are trying to find the norm 1 in norm 1 matrix A, norm infinity of matrix A, and norm 2. For norm 1, that is another name is called maximum column sum. Maximum column sum. Okay, we are finding based on these equations. This is the matrix. We are adding the absolute value of each columns together. Thirteen plus 3 is 16. Again, we are working on an absolute value. And this is 56. And the maximum value is 56. For this reason, for norm 1 of the matrix A, the answer is 56. How we can find the norm infinity of the matrix A? Another name is called maximum row sum. Its meaning we are adding the absolute value of each column, each row separately, and then we pick the maximum value. For the first row, the summation of absolute value is 16. For the second row is 56. 7. The maximum value, this one. For this reason, for this matrix of A, the norm infinity is 57. This is the norm, um, norm infinity. For finding the norm 2, we need to find the maximum of the lambda for A transpose times A. First, we have to make it find the A transpose times A. This is for A transpose. Switching the row and columns. And this is the matrix of the A. And now we find the A transpose times A. Once we multiply these two matrices based on this sequence, okay, the value of A transpose times A will be 178, 136. The next step, we have to find the maximum eigenvalue of this matrix. For finding the maximum eigenvalues for this matrix, we have to subtract the main diagonal from the lambda, and then the determinant of the matrix should be equal 0. It's meaning this is the determinant, 178 minus lambda, that is eigenvalues, should be equal 0. Once we solve this determinant, we have a quadratic equations, and we will have two roots. The lambda one is 171, 271. This is the one of the roots of these quadratic equations, and this is the second root. As you can see, this is as a maximum value, or this is the spectral radius for this matrix, is mean A transpose times A. Now we have to find the roots of these numbers. Once we plug to these equations, the answer is 54.102. This is the answer of the norm 2 of the matrix A. This is the two concept that we have to know. That another concept is about the conditioning numbers. Let's look at these examples. Okay. For this we have the matrix of the A, and this is the inverse of the matrix A. Now we have to answer each of these questions. In question A, find the infinity conditioning number for the coefficient of matrix A. And if then the question B, if the system of equation is well conditioned and has a small residual, the answer is indicate we have accurate solutions. And in practice, is pivoting suggested to solve the given system of the equations? Okay, let's answer these questions. This is the matrix A. And this is about the inverse of the matrix A. Okay, this is matrix A and this is the inverse of the matrix A. The conditioning number is found by this equation. We have matrix norm of inverse times norm of matrix A. For example, for these problems, we have to find the conditioning number, infinity conditioning number for for this matrix. If I rewrite it, the conditioning number for matrix A based on the infinity is this one. How we can find the infinity norm for these two matrices? Once we talk about the infinity norms, is or another name is a maximum row sum. We are adding the absolute value of each columns together, each row together, and then we pick the maximum one. 5 plus 4 is 9. For second row is 13. For third row is 23. The maximum value is 23. I can say infinity norm of the matrix A is 23. How we can find the infinity norm of this matrix? Again, we are adding the absolute value of all the components at each row together. For example, for the first row, the answer is 0.356. Second row, and this is about the third row. The maximum value for inverse of the matrix A based on infinity is 0.356. Now we multiply these two numbers together and this is the conditioning number for matrix of A based on infinity is 8.188. For the conditioning number, we have to know that some things. Okay, if the conditioning number is small, then the small residual is indicate the accurate solution. But if the conditioning number is large, then the system or matrix of the A or right hand side of the equations, okay, is sensitive to input error. And for this reason, the small residual for the system of equations, once the conditioning number is large, it doesn't show we find the accurate solution. One of the reasons the conditioning number is large, okay, because one or more equation is nearly linearly dependent on one or more equations. How we can determine the large conditioning number? The conditioning number is large if the conditioning number equal or larger than 10 to the power 7. This is for the single precision. And if conditioning number is equal or larger than 10 to the power 12 is for the double precision, then this value will be large for the system, and then we will have a ill condition system, is meaning the system is sensitive to the inputs and one or more equation is nearly linearly dependent on one or more equations, and the small residual doesn't indicate we find the accurate solution. This is the three important concept that we have to know that for solving the system of linear and nonlinear equations. First, we start with solving the system of linear equations. If you remember, for solving the system of linear equation, we have two options, direct methods and iterative methods. Once the number of the equation is less than the 2000, we can use the direct method. For the direct method, there is no truncations error, and the only error that we are involving is round off error. And the reason we cannot solve the equation larger than the 2000 is related to the round off error. Once the number of the equation is larger than the 2000, we have to switch to the iterative methods. And we cover the two methods for iterative method in this video, Gauss-Seidel and Jacobi methods. Another things that we have to consider once we are solving the system of equations, okay, uh, first we write we are using the linear algebra, okay? For this reason, we are write the system of equation based on the matrix and vector. The A as a matrix of the coefficient, X as a variables, and the B as a right-hand side of the equations. If the determinant of the matrix of the coefficient is non-zero, then if the determinant of the coefficient matrix of A is non-zero, then we can find the inverse of the matrix of the A, and then the system has a unique solution. But if the determinant of the matrix of the coefficient is 0, then we cannot find the inverse of the matrix A, and the problem is not solvable. Let's look at these examples. And we have to solve these problems based on the Gauss eliminations method as a direct method. Okay, we have to solve these problems based on the Gauss elimination method as one of the direct method. This is the matrix of the coefficient. This is the variables that we have to find it. And this is the right-hand side equations. Okay, the problem mentions without the pivoting on the system of equations, answer the questions. Okay, for finding the for solving the problems based on the Gauss eliminations method, by elementary row operations, we have to make a matrix as a upper triangulars. Then we can find the value of these variables and also the determinant of the matrix. The elements in the main diagonal is called pivot elements. This is the pivot ones, and based on the based on the Gauss eliminations method, all the elements below the pivot should turn to the zero. And how we can turn it to the zero? By elementary row operations. This is equation 1, equation 2, and equation 3. For turning this element to the zero, we have to create the -2 and then we add it together, becomes 0. For this reason, we write this equation a2 minus 2 over 5. This is as a pivot counter 1. Now, once we are applying to the equation 2, then we have 2 minus 5 times 5, that is turned to the 0. This is the next element. And this is about the third element. Okay, this is about the matrix A. This part doesn't change. And how about the right-hand side? Is mean the B. We have 17 minus 23 negative 2 over 5 times 17, 12. If I rewrite these equations, right, based on the final answer, we have 503 And again, this part is about the B. Okay, as you can see, this is the pivot one. This element turn to the 0. The next one, this element also should turn to the 0. Again, by applying the elementary row operations, okay, we turn this element to the 0. Is meaning we have to create the negative 3. 3 minus 3 becomes 0. 3 over 5, equation 1. Once we are applying to this equation, this is the first row. This is about the second row. And now we have to find the equation 3 based on this. Okay, we have 3 minus 3, 5 times 5. That is turned to the 0. 4 minus 3 over 5 times negative 2. 8 minus, and this is 1. And this is about the B. Okay, if I rewrite it again, we have 5, 0, 0, negative 2, and this is about the B or right hand side. Okay, see, this is the pivot 1, pivot counter 1, and all the elements below this pivot is turned to the 0. Now this is the pivot counter 2. Okay, now all the elements below this and this element should turn to the 0. Again, by applying elementary row operations, we turn this element to the 0. Okay, we have equation 3 minus, we have to create the negative 26 over 5 based on these elements. By simplify, we have equation 3 minus 26. Okay, now we are adding, we find the equation 3, okay, based on this. We rewrite is meaning. This is equation 1 and 2. It doesn't change. Now for equation 3, okay, we are using this, okay. We have 0 minus this coefficient times equation 2. The value is 0. This is keep as a 0. Now we have 26. Also, this is turned to the 0. The next one is element 37 over 5 minus times equation 2. This is about the matrix of the coefficients, okay? And this is about the B. We have 9 over 5 okay? Now we rewrite this one based on the fractions, okay? Based on the decimal number. 5, 0, negative 2, 1, 17. 39 over 5 is 7.8, negative 3.4, negative 149 over 5 is negative 29.8, 0, 0. As you can see, now the matrix of the coefficient become as the upper triangulars, okay? And by back substitutions, we can find each of the variables, okay? If I write the variables here, it's meaning this is x1, x2, x3, and this is the right hand side. Okay, now by back substitutions, we can find the value of each of these variables. We have 9.66 x of 3 equal 21.66. This is the value of the x of 3. From equation 2, we have 7.8 x sub 2 times x2 plus, negative 3.4 x sub 3 equal negative 29.8. If I substitute the x sub 3 in the equations, okay, then the value of x sub 2 becomes negative 2.84. And from equation 1, we have 5 times x sub 1, negative 2x sub 2, x sub 3 equal 70. If I plug each of these variables, is mean x sub 3 and x sub 2 here, okay, then we can find the value of the x sub 1. Okay, now this is the answer. The value of the x, the vector of the x is 1.814. Okay, Based on this upper triangular matrix and the vector of the x, okay, um, we answer the questions, okay. For part A, we have to find the A, and we have to find the value of this. A, 2, 3, once we make the matrix as a triangular, okay. To how we can find it, this is talk about the row and this is talk about the columns. Second row, third columns, okay. And the value is negative 3.4. For part B, we have to find the value of the B sub 3, okay. It's meaning the right hand side and about the third equations. The value is 21.66. For part C, the value of the x sub 2. If you look at the vector of the x or our solutions, the value of the x for the second variables is negative 2.84. For question D, okay, one solution is given. Okay, this is part D. Suppose someone used the Gauss eliminations method and they computed the solution to be x as a vector of the x as a 15, 25, and 5. And using the infinity norms to calculate the norm of residual vector. Its meaning, we have to find the infinity norm of the residual based on this answer. How we can find the residuals is ax minus b. Okay, now we have to plug to the main equation or our original equation. This is the a, this is the x, and this is the b. The residual is, this is the matrix of the A or matrix of coefficient. This is the solution minus. Once we solve these systems, is meaning multiple this matrix to the vector, then we have a vector by dimension of 3 times 1. Then subtract from this vector, and the answer is 13, 213, 173. The infinity norm of the residual for these problems based on this answer is 213. Okay, this is the answer of the part D. For for the next part, the conditioning number for this system is given as a 3.52. And also is mentioned combined with the norm of the residual that we calculate from the part D. Okay, we have to answer this question. The solution is not accurate because the conditioning number is low, but the residual is high. This is correct. Okay, see the conditioning number is as a low because in the review parts, okay, I mentioned for conditioning numbers, if larger than this value, okay, we will have a ill condition and the conditioning number is large. But the conditioning number for this problem is given as a 3.52. For this reason, this one has a conditioning number for this problem is low, but the residual residual based on these solutions, okay, is high. For this reason, the solution is not accurate. And that makes sense, okay? Because the exact answer of these three system of linear equation, these numbers, okay? But and the solution that is given, these numbers, okay? And there's a very big difference, okay, between the exact answer or true solutions with the number that is given. And the last one is about the floating point operations, okay, for solving these problems, okay? For solving the problems based on the Gauss eliminations method, we have NQ, okay? For example, for these problems, we have three system of linear equations. The value of the N is 3. 3 to the power 3 is 27, is the total number of the floating point operation for these problems. Okay. The next example is about solving the system of linear equations based on the iterative method. The first example is about the Jacobi methods. The matrix of coefficient is given, and this is about the right-hand side. The initial guess is given because once we are solving the problems by iterative method, we need the initial guess. And we have to answer all of these questions. This is the matrix of the coefficient. And this is about the right-hand side. And this is about the initial guess. Again, the superscript is talk about the iteration level. Is given as a 1, 1, 1. We have to solve this problem based on the Jacobi method. For solving these problems based on the Jacobi methods, okay, first write these three system of equations, okay. It's meaning we have 8 times x1, 10 x2, 5 x sub 3 equal 20. The equation 2 is 2 times x1, x2, and this is about the third equation. Okay. Now for the Jacobi methods, okay, we rewrite it. From equation 1, we find the value of the x1. From equation 2, we can find the value of the x2 and so on. We have 20 minus all the elements except x1 is move or shift to the right side. 10x2, 5x3, and as you can see the coefficient of the x1 as a 8, we have to divide it to the 8. How about the x2? We shift all the elements except x2 to the right side. As you can see, the coefficient of x sub 2 is 4. And this is for equation 3. And again, the coefficient of x sub 3 is 6. Okay. Now we rewrite these three equations that by this format we can apply the Jacobi method. The initial guess is given 1, 1, 1. Now we have to answer each part of the questions, but just I want to add one part, okay? Find the infinity residual. Again, this part is added to the problems, okay? Find the infinity norm of the residual for initial guess. Okay, it's meaning we have to plug the initial guess to the equations, okay, and find the residuals, okay. Again, the residual is found based on ax minus b. You can write the matrix times vector minus b, or you can directly plug to the equations. We have 8 times of 1 minus b. This is about the equation 1. The answer is negative 7. For equation 2, when we plug the initial guess, minus b is negative 25. Again, don't forget to subtract this part from the b. We have ax minus b. And this is about the third equation. Minus b, the answer is 3. We have to find the infinity norm of the residuals. This is as a vector. The infinity norms is talk about the maximum value. For this reason, Therefore, our answer is 25. Okay, again, this is the extra parts. Okay, now look at the problems. For part A, we should find the value of the element x of 1 after one iteration. We are working on these three equations, okay, to find the value of the x of 1. 20 minus 10 times 1 over 8. This is 1.875. This is the first iteration. Okay, the answer of the part A, this one, the value of the x1 after one iteration is 1.875. For part B, we should find the infinity norm of the residual vector after one step of Jacobi iterations. Okay, for finding the residuals, we have to find the value of the x2 and x3 for the first iterations. The value of the x2 for first iteration of the Jacobi is 7.25, and this is about the x of 3. Okay, this is the vector of the x for after the first iteration. 1.875, 7.25.5. For finding the residuals, okay, the initial residuals, okay, we have to find ax minus b. We plug these numbers to the three main equations. Again, ax minus b minus b. Okay, this is the answer. And for finding the infinity norm of the residual, we have to pick the maximum absolute value. The answer is 65. This is the answer of the part B. For part C, we have to find the value of the x sub 1 after the second iterations. For finding the x1 for the second iteration, we are using the vector of the x for the first iterations, okay, and plug it to these three rearrangement. We have, this is the x1 for the second iterations is 20 minus the value of the x2 for the first iteration over the, I'm using these three equations. The answer is negative 6.25. The value of the x2 for second iteration, again, superscript is show the iteration level, equal, we plug to this rearrangement, and this is the value of the x3 for the second iteration. Is 3.958. Okay, the answer of the part C, the value of the x1 for the second iterations based on this solution is negative 6.25. This is the answer of the part C. Okay, let's look at the next part. Um, okay. Sorry, for part C, we have to find the value of the element x of 2 after the second iteration or after two step of the Jacobi. It's meaning the answer of the part C will be 6.6875. Another things I want to mention here, okay, the Jacobi method as a parallel method. Parallel computations method. Okay. This is the answer of the question. Let's look at the next problems. This system of linear equations is given, okay, and we have to apply the Gauss-Seidel methods and answer each of these part of the questions. Okay, this matrix of coefficient, this three system of equation is given, and we have to solve based on the Gauss-Seidel method, another iterative method. This is the matrix of coefficient. And this is about the right hand side vector. This is the initial guess. For part A, we have to find the value of the x of 2 after one iterations. Okay, and for part B, find the residuals after one step of the Gauss-Seidel iteration is applied to the systems, and so on. Okay. For the Gauss-Seidel method, like as the Jacobi method, first we have to rearrange the equations. First, we write these three system of equation. We have 4x1 okay? Then we rearrange. From first equation, we can find the value of the x1. We have 4 minus 2x2 over 4. This is the value of the x, and this is the rearrangement based on the equation 2 over the coefficient of x2 over 4. Okay, first we have to find the value of the x1, okay, for the after one iterations. We plug the initial guess to these three rearrangements. The value of the x1 for the first iteration is 4 minus 2 times 0 is the value of the x2 for the first iteration is 6 minus. This is the Gauss-Seidel method. Okay, use the most recently updated solution value. Okay, it's meaning um, we are not using for the second equations. We are using the recent update of the x1. For this reason, we have minus 1 plus 3 times 0 over 5 is 1. The value of the x3 for the first iterations is 3 minus, we are using this updated value minus the updated value of the x of 2 over 4. The answer is 1 over 4. As you can see, okay, the Gauss-Seidel method uses the most recently updated solution value. For this reason, this method is faster than the Jacobi method if the algorithm is converged, and if the solution diverges, the Gauss-Seidel method diverges faster than the Jacobi method. Now this is the vector of the x for the first iteration is 1,1.25. The answer of the part A, find the value of the x2 for the first iteration. The answer will be 1. For part B, we have to find the infinity norm of the residual after uh, after the first iteration. How we can find ax minus b. Now we are plugging these solutions, okay, to these three system of equation, or you can write a times this vector minus b. Both is correct. We have 4 times minus b. This is for equation 1. This is for equation 2. Minus b. And this is equation 3. For finding the infinity norm of the residual, we have to pick the maximum absolute value, and is 1.75. This is the answer of the part. Again, for the residuals, you can directly plug your answer to the equations, or you can do this process. Okay, this is the matrix of the coefficients. This is our solutions is 1.25. Pre-multiply this matrix of the coefficient to the answer minus b. We will get the same answer, and then we pick the maximum value. For part C is asked after carrying out 2 steps of the Gauss-Seidel iterations, the value of the x2, what's the value of the x2? Okay. This is part C. This is the vector of the x after the first iteration. And now we plug to this rearrangement for finding the value of the x2. Okay. The value of the x1 for the second iteration is 4 minus over 4. The value is 0.5625. The value of the x2 for the second iteration. Again, this is show the iteration level is 6 minus the value of the most recent updated value of the x1, 5625 plus 3 times 0.25. Okay, this is the value of the x2 for the second, after the second iteration based on the Gauss-Seidel methods. Again, be careful about these methods. These methods, okay, use the most recent updated value, okay. But about the rearrangements of the equation, look at the Jacobi methods, okay. And both of the methods, okay, is some part is same, okay. They need the initial guess, and also we will rearrangement the equations, okay, based on the variables and then plug it, okay. But Jacobi as a parallel method, but the Gauss-Seidel is not as a parallel method. This is about the answer of the part C. For part D, the question of the part D, do you have any guarantee that the Gauss-Seidel iteration will converge for any initial guess? For checking this one, we have to look at the um, matrix of the coefficients. If the matrix of the coefficient is diagonally dominant, okay, then we can say the system will be converged, okay? Look at the matrix of the A, the matrix of the coefficients of the problems. Okay, if you, this is about the all the elements in the main diagonal for checking the diagonally dominant or not diagonally dominant. Okay, we are checking these conditions. The absolute value of the 4 should be larger than the summation of absolute value of other components. This is also larger. Okay, now we can say the matrix of the coefficient is diagonally dominant. Therefore, the solution will be converged. This rule also apply for the Jacobi methods. Okay, and the last part, this is a part D. Okay, the last part is about the floating point operation of these methods. Okay, the problem mentioned if it took 20 iterations, okay, that the solution is the residual vector, for example, meet the tolerance that defined by users, okay, determine the number of the floating point operations for these problems. Once we are using the iterative method, the total floating point operation is found based on this equation, kn square. This rule is true for the Jacobi and Gauss-Seidel methods. Okay, the problem mentioned after 20 iteration, the residual meet the tolerance. How about the n? N is talk about the number of the equation of the systems. Okay, now we have a three system of linear equations. This is 3 to the power 2. Okay, and the answer is 180 floating point operation. But if you remember, okay, for the Gauss eliminations method, that is direct method, the floating point operation is n cubed. Please don't confuse these methods together. Okay, this is the floating point operation for the Jacobian Gauss-Seidel, and this is the floating point operations for the Gauss eliminations method. Okay, this is the some points that we have to note that for these two iterative method. For system of linear equation, if the matrix of the A is diagonally dominant, we can guarantee that Jacobi or Gauss-Seidel iteration will converge for any initial guess. And the next one, if the magnitude of the eigenvalue vector for the iterative matrix, is meaning the Gauss-Seidel matrix or Jacobi matrix is less than 1, we expect that the Gauss-Seidel or Jacobi iteration will converge to the solution. For example, if the eigenvalue vector for the iterative matrix of the Jacobi is these numbers, determine the spectral radius for these eigenvalues, and do you expect that the Jacobi iteration will converge to a solution? As you can see, the spectral radius for this Jacobi matrix is 1.365, and this is larger than the ones. Okay, for this reason, no, because the spectral radius is larger than the one, and we cannot guarantee. This is the points that we have to know, some points that we have to know that for the Jacobi and Gauss-Seidel methods. Again, please don't confuse the Jacobi and Gauss-Seidel methods. Okay, the Jacobi method as a parallel method, but the Gauss-Seidel method is used most recently updated value solutions. The last question is about solving the nonlinear system of the equations. This nonlinear system of equation is given, and now we have to solve based on the Newton-Raphson method. Solve based on the Newton-Raphson method. This is the equation 1. And this is equation 2. And the initial guess is given 2 and 1. For part A, we have to find the J sub 1, 2. Okay. As a general, once we are trying to solve the nonlinear system of the equations, okay, we are trying to make it as a linear systems, okay, by Jacobians for making the Jacobian matrix and this is the Jacobian matrix for matrix 2 by 2, the partial derivative of the equation 1 respect to the first variables respect to the second variables. This is the partial derivative of the equation 2 respect to the first variables respect to the second variables. This is called Jacobian matrix. Then we have this vector. Just I show for 2 by 2 or for two nonlinear system of the equation equal negative of the equation 1, the value of the equation 1 at the value of the vector of the x at nth iteration. Okay, then we can rewrite these equations as a Jacobi matrix times this is show delta x for nth iterations f of x n. First, we solve the equations. The first step, solve the linear system. For delta x n, okay, and then update the solutions based on this. Xn plus 1 minus xn equal delta xn. And now we can find the value of the x for n plus 1 iteration. This is about the Newton-Raphson method, okay? In practice, has a 2 steps. First, we find the delta x, then we can find the value of the x for n plus 1 iterations. If I want to write the Jacobian matrix, as a general, okay, we have Jij is talk about the partial derivative of the equation I respect to the j variables. Now for these problems, okay, this is just as a quick review, okay. For these problems, we have to find j sub 1, 2 is meaning the partial derivative of equation 1 respect to the second variables. This is our equation 1. Now we take a partial derivative from the second variables, is meaning x sub 2. This element, this term doesn't have the x sub 2. How about this? We have negative 9x to the power 2. And the value of the x2 for the initial guess is given as a 1. Okay. This is the answer of the part A. For part B, we should find the infinity norm of the residual for initial guess. Okay, for initial guess. We plug this value to these two equations. We have 2 times 2 minus 3 times 1 to the cube. The answer is 1. This is the residual for equation 1. And this is about the equation 2. And we have to find the infinity norm of the residual, is meaning the maximum value, because this is as a vector. This is the answer of the part B. For part C, we have to find the value of the x1 for the first iterations after the one-step iterations. Okay. The first step, we have to make a Jacobian matrix. Okay. This is the general equations, okay, for Jacobian matrix of these problems. The derivative, the partial derivative of equation 1 respect to the x1 is 2. Respect to the second variables is negative 9 x2 square. This is 2x1, and partial derivative of equation 2 respect to the second variables is 2. Okay, this is the Jacobian matrix for these problems. Okay, and for each iterations, we have to update this value. Now, for first iterations, okay, we have to find the Jacobian matrix based on the initial guess. If I plug the initial guess to the Jacobian matrix, we have 2 times 2 as a constant, negative 9. The initial guess for x sub 2 is 1. 2 times 2 as a 4. Delta x1, delta x2 equal negative of f of x1, and the first two and the two equations at the value of the equation at the initial guess. This means 2 times 2 minus 3 times 1 cube. Okay, the answer is 1, but we have to multiply to the negative. Now we have delta x1, delta x2. If we multiply the whole of this equation to the inverse of the Jacobian matrix, okay, and this is the inverse of the Jacobian matrix. And -1, -6. Once we solve this one, first row times the columns, okay, is equal delta x1. Okay, this is about the delta x1 and delta x2 second row times this vector. Negative times negative is positive. 0.05 times -6. Now delta x1 is, the answer of this one is -1.4. Delta x2 is -0.2. And delta x1, okay, for these problems is x1 for first iteration minus x1 for initial guess is showing delta x1. Okay, now we can say x1 for first iteration is equal. The value of x1 for initial guess is meaning 2 plus the delta x. The value is 0.6. And the value of the x2 for first iteration is the value of the x2 for initial guess, that is given as a 1, plus delta x is 0.8. Now the vector of the x for the first iteration is 0.6, 0.8. Again, this is the inverse of the Jacobian matrix, okay? Because for finding delta xn, we need the inverse of the Jacobian matrix times negative of f of xn. This is the answer of the part A, okay? It's meaning for part A, the value of the x1 for the first iterations is 0.6. Sorry, this is the answer of the part C. Okay. For part D, after carrying out one step of Newton-Raphson iteration, the infinity norm of the we should find the infinity norm of the residuals. For finding the infinity norm of the residuals, for the first iterations, we are plugging these values to the equations. And then we pick the maximum value. We have to find norm infinity. The answer of the infinity norm of the residual for the first iteration is 1.96. The next part is after the second iterations of Newton-Raphson method, we should find the value of the x sub 2. For finding the value of the x sub 2 for the second iteration, the first step, we have to update a Jacobian matrix based on the vector of the x for the first iterations. The second iteration, we have to update a Jacobian matrix based on the vector of the x for first iteration. We have to this is 0.8 to the power 2. The answer is 1.22. Okay, this is about the Jacobian matrix. Now we have Jacobian matrix. Updated value of the Jacobian matrix for the second iteration. Delta x1, delta x2, negative the value of the function, the two function um, at the vector of the x for the first iterations. Okay, again, don't forget to multiply the f of x to the negative. Now we have to find the delta x. For this reason, we need the multiple the whole of the equation to the inverse of the Jacobian matrix. It's meaning delta xn is the inverse of the Jacobian matrix times f of xn. This is the inverse of the Jacobian matrix. This is the negative of f of x minus times negative times negative is positive. Negative times positive is negative. And once we solve this part, is meaning matrix times vector is negative 0.973, negative 0.396 is meaning delta x1 equal 73, and it's talking about the value of the x1 for the second iteration minus the value of the x1 for the first iteration. The value of the x1 for the first iteration is 0.6, and once we solve it, the value of the x1 for second iteration is negative 0.373. How about the delta x2? Delta x2 equal negative 0.396 is talking about is meaning x2 for second iteration minus x1, x2 for the first iteration equal negative 0.396. The value of the x2 for the after the one iteration or for the first iteration is 0.8. Once we solve this one, the x2 for this, the value of the x2 for the second iteration is 0.404. This is the answer of the part E, okay? The value of the x2 for the second iteration. Again, this is talking about the iteration level. Is 0.404. Okay. This is the process for solving the nonlinear system of the equations based on Newton-Raphson method. For example, for third iteration, the first step, we have to update it, the Jacobian matrix for these problems based on these vector. Is meaning we have to update it, the Jacobian matrix, okay, for these problems, okay, and then we will do all of these steps like as the iteration 1 and iteration 2. This is the review of system of linear and nonlinear system, nonlinear equations system, nonlinear equations, okay, and thanks for watching.